Just want to look at just a couple of ones that appeared over the years, some different types of ones. Now, we only deal with constant angular velocity. But here's a question where it was actually variable angular velocity. It still was constant because what we've got is this train moving around a circular track, and it is constant angular velocity around the track. But if we change the reference point to over here, n, this angle here, which has been labelled phi, won't be constantly changing. It'll be variably changing. And so that's what the idea of this question was thinking about how does this angle change rather than the one at the centre. So they define it for us as moving at u metres per second and all those sorts of things. So the first part was simply, well, I say simply, let's see how simple it was. Express the theta to t in terms of a and u. Well, we know the length of the arc is equal to the radius times the angle at the centre. Now, the picture we have, the radius was a, and the length of the arc we have called L. So L equals a theta. Differentiate both sides. I get dl dt is equal to a times the theta dt. In other words, it's just our v equals r omega, but using derivatives. dl dt, they told me it was travelling at a velocity of u. So I subbed that in. And then it's just rearranging that, making the theta dt the subject. And there we go, we've got our expression u over a. So the first part, not too bad. Bit of a gift mark to start the question off. Before we got to this bit. Right, it looks incredible. Show that a sine theta minus phi minus x plus a theta sine phi is equal to 0. And if that's not enough, we're then going to deduce this derivative because, it's... Well, play around with a bit of geometry here. I've got to define some angles. I know NTO and TNO, they all add up to be the angle TOS, exterior angle of a triangle. So subbing in the angles, there were TNO, that's what they've labelled with phi. TOS, that's what they've labelled with theta. So why have I done that? Well, I knew I had to find an angle somewhere that is theta minus phi. So NTO would be that angle that is theta minus phi we need for this question. So now I'm looking at triangle NTO, and it actually drops out quite nicely. All I now do is use the sine rule. A over sine phi will be a plus x over sine theta minus phi. Cross multiply, and then move everything to one side, and we get the result that they're looking for. So it was actually just a use of the sine rule. The trick, of course, was finding out which angle. If you didn't recognise that NTO was the angle theta minus phi, well then, obviously the question would have become a lot harder. Recognise that, drops out quite nicely. Still got to differentiate, though. Okay, so I'm going to differentiate that expression with respect to t. Now, I'll just go backwards so I can see the expression I'm differentiating. Probably should have written that down, it would have helped. So I've got to differentiate a sine theta minus phi. Well, I can't differentiate it with respect to time, but I'm going to differentiate it with respect to theta minus phi. But remember, we have a rule that says when we're differentiating terms, we can differentiate them all at once, theta minus phi, or I can do them one at a time. So to theta to t minus to phi to t. So when I differentiate with respect to theta minus phi, I would multiply it by, let me write it over here so it's a bit more obvious. It's that chain rule, implicit differentiation. I would have multiplied it by d theta minus phi dt. But as I'm saying, I can break that derivative up into two single derivatives. Because with differentiators, saying if you've got two terms, you can do the whole function at once or do it a bit at a time. So I'm going to multiply it by d theta to t minus d phi to t, because these are expressions I need in what we're trying to prove. Then the other term, minus a plus x. Again, let me just go back to the original function. Well, sine phi, again, I can't differentiate it with respect to t, so I'll differentiate it with respect to phi, multiply by the phi to t, implicit differentiation. Well, sine goes to cos. And on the right-hand side, well, that's easy. Differentiate 0, you get 0. So, the phi to t. Well, there's the phi to t in this one, and there's the phi to t over here. So I'm going to have to expand that out. And I've grouped the phi to t's together. So I have a cos theta minus phi d theta to t minus a cos theta minus phi d phi to t, but I've also got a minus a plus x cos phi d phi to t. Group those together with the phi to t, because at the end of the day, I want to get the phi to t by itself. Right, move the expression with the theta to t over, but you'll notice I've done something else. Remember back in the first part, we showed that the theta to t was u over a. We've had an expression for the theta to t. So I've substituted that in. Now I want to make the phi to t the subject, so I'll divide, and I've come up with the expression that they're looking for. So that one was a little bit more involved than the other bit. But the nice thing about it was that, hey, they gave you what it is you were trying to prove, so it didn't stop you from going on and doing the next bits if you couldn't come up with that result. Right, so we're going to show that that rate of change is equal to 0. In other words, there is no change in the angle when nt is tangential to the track. So I've just redrawn the diagram over here, well, leaving out some bits of information, but drawing in that nt is now a tangent. Well, if nt is now a tangent, ot must be perpendicular to it, because radius is perpendicular to tangent. So I now know, okay, that's a right angled triangle. So that was the angle, remember we said nto was theta minus phi. So theta minus phi back here with the phi to t, remember we're trying to prove is equal to 0. Forget about the bottom of the fraction, have a look at the top of the fraction. We're now saying u cos 90. And the cos of 90? 0. So u cos 90, we've got our result, it's just equal to 0. So really what we needed to do in that question, it was showing that that angle was 90 degrees. Once we got that being 90, it drops out. Suppose that x equals a. So it's the same distance as the radius. We're now going to show that its angular velocity about n, when theta is pi on 2, is 3/5 the angular velocity when theta is 0. So let's look at the two cases. Theta is now pi on 2. Well, if theta is now pi on 2, we have this situation. NOT, again, it's a right angled triangle, but now the right angle is at O. And we define TNO to be phi, and so that theta minus phi up there will now be 90 minus. So A is OT, ON is 2A. Hypotenuse, root 5A. So cos phi, I know, is 2 on root 5. Cos of 90 minus phi, so the other angle over here, would end up being 1 on root 5. Subbing into our formula. So there's our formula. U cos pi on 2 minus phi, A cos pi on 2 minus phi, plus 2A cos phi. Remember that was A plus X, but we've said X is equal to A. Subbing in those ratios we just worked out, 1 on root 5 and 2 on root 5. The root 5s are all going to cancel there. I end up with u on 5a. So, okay, I know the angular velocity when it's equal to pi on 2. Hopefully we can show that this is going to be 3/5 of our next answer. Let's have a look when theta is equal to 0. Theta is equal to 0. Let's sub in the phi to t. We end up with u cos 0 plus a cos 0 plus 2a cos 0. If theta is equal to 0, because what we're now saying is NOT or NTO, depending on where t is, but it's now a straight line because there is no angle there. So all of those angles, if you like, are now 0, or you could think of them as pi, I suppose. But u cos 0 is, of course, 1. I just get u on 3a. Well, is that 3/5 of that, or 5/3, which way round? Let's have a look. Yes, well, that is 5/3 of u on 5a. So yeah, the angular velocity at pi on 2 is 3/5 times the angular velocity. So, well, quite a lot involved in that question. Right. Let's have a look at another year. Lovely, lovely question. A string of length L. So we're now talking about a vertical circle. But what's really exciting is, look, do you know what this is? I know it just looks like a question, but think about it. You've got a string of length L, and you're going to spin it in a vertical circle. Can you think of a situation where you do that? A yo-yo! As you got your yo-yo. Yeah. But then you do that really good trick around the world. You know the one? Gee, I wish I had a yo-yo right now. It's all right, we're going to attempt to spin it in a vertical circle. They've told us we're going in a counterclockwise direction. They've defined velocity to be ds to t, because the length of the arc they've called s rather than x. What else have they told us? They've given us the angle at the centre, length of the string. We're going to assume there's no frictional forces acting on P. I guess that makes sense because the yo-yo's in there, unless they're thinking that there'd be some rubbing between the string and the yo-yo. But so they're saying neglect that. For parts A to D, we're going to assume we perform the trick, that the mass does indeed move along the circle. We got to prove this wonderful expression there for acceleration. Now, it looks very different, but all it really is, watch. We know S is equal to L theta. S, length of the arc, L, radius, theta, angle at the centre. Velocity is ds to t, so that'll be L times d theta dt. Acceleration then is dv dt. Dv dt I can write as dv d theta times d theta dt, because I notice over here I need to get d theta into here. So I've changed my dv dt into dv d theta, but to balance it out I've got to multiply it by d theta dt. Well, d theta dt I can write as v on L. Oh, that's good, because now look, I've got the 1 on L, I've got the d theta. What's missing is the half v squared. Well, v I could rewrite as d dv over half v squared. The dv's now cancel, and I get 1 on L, d d theta over half v squared. Basically, it's the same way that I proved d dx over half v squared. It's just using different pro numerals and what have you, but it's the same idea that I did there. But again, they've given us that expression, so had we not been able to come up with that, at least we've got the expression we can use and move forward to part B. We're now going to show the equation of motion of P is this beautiful expression, 1 on L, d to theta over half v squared is equal to minus g sine theta. By changing all these letters, it throws people out of their comfort zone. And they think, oh, I've never seen anything like this. But you have, because there's good old Bob. Okay. There's tension in the string, which I've conveniently made a horizontal force. I'm considering the particle when it's right out here horizontally. However, right, so I've rotated the problem like I did yesterday. I wanted to make tension a horizontal force. Okay. So I have a component of gravity from the picture that they've given me. And if I have a look at the forces now that appear to be downwards. So that's why I turned the problem. By turning the problem, I get rid of the component of tension, because there's no tension in my answer there. ms double dot will equal minus mg sine theta. Normally I'd say mx double dot, but remember they're using s instead of x for displacement. So I'm saying the resultant, mx double dot, in this case ms double dot, is equal to minus mg sine theta. All right, well, my masses are going to cancel. So what have I got? I've got d2 s to t2 that we just proved was 1 on L d to theta of a half v squared. So all it was really asking me to do was to resolve some forces and come up with that expression. Okay. Deduce capital V squared is little v squared plus 2gl 1 minus cos theta. All right, we now have this expression I can play with. Oh, well, just multiplied by L. I didn't do it the definite integral way this time, so I've just integrated both sides, but I've got plus a constant. So half v squared is gl cos theta, multiply both sides by 2. What's the initial condition? I know, well, I know when theta equals 0, v was equal to capital V. So capital V squared is 2gl plus c. There's my constant, v squared minus 2gl. So I have little v squared is equal to 2gl cos theta plus capital V squared minus 2gl, but they want capital V squared to be the subject. So rearranging all that, making capital V squared the subject, we come up with the expression. Explain this. Oh, I know you love these ones where you have to actually explain rather than do your maths. You sort of actually, do you understand what this problem is doing? So tension minus mg cos theta is 1 on L mv squared. Well, back when I did my force diagram, I only did the vertical one. Let's have a look at the horizontal ones, and I think the explanation actually will just turn out to be doing some maths. So tension, remember, we said was going to be purely horizontal when we turned the picture. We'll have a component of gravity going to the right-hand side, mg cos theta. The resultant force, but it'll be circular motion, and it'll go towards the center, which of course is in the same direction as the string. So I know mx double dot is tension minus mg cos theta, but that resultant force is centripetal force. So this is me explaining. So I thought I'll throw some words in there. So mv squared on L is equal to t minus mg cos theta, and then playing around with it, we get the expression that they want. Now, the interesting part of the question, because if you recall, it said in parts A to D, we can assume that our yo-yo travels in the circle. Guess what happens now? We're going to suppose that v squared is 3gl. We're going to find the value of theta at which the t equals 0. T equals 0. Well, we're going around in a circle, spinning the yo-yo. At some point, tension is going to equal 0. What does that mean? Yeah, it's no longer moving in its circle. The string has gone slack. See, whilst it's in the circle, the string's nice and tight. It's going around the lovely circle. As soon as tension becomes 0, it means, whoop, there's no more slack in this. I mean, it's not, say that again. The string's no longer tight. It's now slack. So there's no tension in the string. So it moves out of its circular motion. All right, let's find that value. So we'll sub in for v squared. We're going to sub in 3gl. We're going to make tension equal to 0. And eventually we'll get cos theta. Okay, there it is. It's when cos theta is equal to minus a third. So I've got the answer in radians. 1.911 radians. Around about there. Once we spun at 1.911 radians, that's when the string's going to go slack. Explanation time again. Consider that situation. Briefly describe in words the path of P after that tension becomes 0. So you're spinning it. Uh-oh. String's gone loose. It's no longer moving in a circle. What will happen? Got to be a parabola. Because it's now projectile motion, yes. Because the string, it's like the string's not connected, tension 0. So all we now have got is an object in the air that has just been projected with a velocity and an angle. It must perform projectile motion. So t equals 0, it's going to undergo projectile motion. It's now going to, instead of going in a circle, it'll go in a parabolic arc. Its initial velocity will be tangential to that point where tension became 0. Magnitude, now I might have got a bit carried away here. I found all sorts of things out and I said, well, okay. And its magnitude, I know it said briefly describe, but hey, forget that, let's show off. Okay, so let's work out what the velocity would be. The velocity turns out to be the square root of GL on 3. I don't think they really wanted to know that bit, but who cares? And then let's draw a picture as well. So, we're starting down here. We're spinning our yo-yo, and we go around in a circle till we get to 1.911 radians. At that point, we're going to shoot off like a parabola in projectile motion. Whee! But then what's really cool is at some point, if you think about it, it's still connected to that string. The string's going to go tight again because it'll come out of the parabola, but then it'll want to keep going, but the string's going to stop it keeping going. Tension's back in the string, so it'll go back to moving in the circle. Have you ever seen someone unsuccessfully do round the world? It's what the yo-yo does. It goes, gee, I wish I had a yo-yo right now. I wonder if I can find one somewhere. 2003. This is projectile motion, but adding some more interesting bits to it. Because, of course, we said whenever something moves, there is resistance in the opposite direction. Now, in 3 unit, we don't think of resistance. We just have a lovely motion and it becomes a parabola. In reality, it's not. Because you would have resistance in the opposite direction. So they've given you the formula, whatever the plural is. So instead of x double dot being 0, we're saying, no, there would be resistance in the opposite direction. So it's minus constant times its velocity. And the same with gravity. Gravity. The same with the vertical. Instead of just being gravity, there's also going to be resistance in the opposite direction. So we've got k times y dot. The bit in parentheses is very important. People can waste time doing things they don't have to. You don't have to show these. These are given to you. You can use them. All right. Derive the result. This is now going to be our equation for horizontal velocity. So dv dt, or dx dot I've used here, is minus kx. So this time I am using a definite integral. So t will end up being, the initial velocity was u cos alpha. That hasn't changed. That's still the same as normal. Dx dot on x dot, it's a log function. So we get minus 1 on k log of x dot, subbing in. Now that's t as a function of x dot. We want to make x dot the subject. Multiply by k, exponentialize both sides, and we get our expression for horizontal velocity. Verify. So rather than getting you to derive it, they've told you what the vertical one is. So all you really have to do with this is, I guess, differentiate it and show that it comes up with the expression they gave you for y double dot. Although I didn't read that, and I went the long way and actually proved it because it's fun. So it's y dot to t is minus ky dot minus g. Again, initial velocity, u sine alpha, vertical direction. Another log function we get when we integrate. That's t as a function, t is a function of y dot. I want to make y dot the subject. Eventually, I get there. Elamont, no, it's still going. There it is. As I say, that was probably not the best way of doing it. I should have just differentiated that with respect to time, similar to what we do when we were proving simple harmonic motion. Remember, we started with displacement in that case, differentiated it twice and said, oh, look, it works. Probably should have done that with this one. Find the value of t when it reaches its maximum height. Well, that doesn't change. Maximum height's still going to happen when y dot equals 0. So we just have to solve that. I'm doing it via, I'm not doing the whole integral again. All I'm doing is jumping back to when I was doing my proof. So I guess this was an advantage of actually deriving the y dot formula. At that point, and somewhere in my working out, I had t equals. I had a formula to work out t. And I'm just substituting in 0 for y dot. So whilst I wasted time in part B, I've ended up saving time in part C. So subbing in 0, subbing in u sine alpha. There we go. There's an expression for t. Beautiful expression too. If you were randomly guessing it, I'm sure you would have come up with that. What is the limiting value of the horizontal displacement of the particle? What we're talking about is the limit as t approaches infinity of this expression here. Because dx to t we know is u e to the minus kt, so x would be the integral. And if it was possible to go to the, I really should have had 0 to t there rather than 0 to infinity, because it's as t approaches infinity. Integrate the e to the minus kt. So what have we got? We've got an exponential curve, but it's our backwards exponential curve. And as that approaches infinity, our backwards exponential curve approaches 0. So, got e to the, I still haven't subbed it in. Let's sub it in. There we go. But then when we sub 0 in, we get 1. So we've got u cos alpha over k.